Hi, I'm Thomas Leonard, and today I'd like to talk to you about OCaml-CI, which is a new CI system we've built at OCaml Labs specifically for testing OCaml projects. I'll start by giving a brief introduction to the CI and a short demo, and then we'll look at some of the unusual features that the CI provides. Then, in the second half of this talk, I'd like to go over some of the technologies that we've used to build it. The cat and Proto RPC system, a new opam dependency solver, the OCurrent Pipeline language, and the OCluster build scheduler. So OCaml-CI itself is a CI for OCaml projects that does not require any specific configuration. Once you've told it to provide CI for your GitHub repository, it will look at your project's existing opam and dune files to work out what to build and which platforms to build it on. And it uses caching to make this fast. In particular, if you don't change your opam files, it will not need to reinstall the dependencies. It's currently in beta, and it's deployed on around 100 GitHub projects at the moment. So just to show an example of the CI being used, I'm going to create a test pull request now. And as we can see, the CI is now building it. And when we go to the web interface, we can see a list of all the builds that it's doing at the moment. You have to press refresh to get updates. But as you can see, we're building on a variety of platforms and we're doing them fairly quickly. So that took about 10 seconds to build on Alpine, Debian, Fedora, OpenSUSE, and Ubuntu with a range of compiler versions from 4.08 here to 4.11. And also on x86-64, which is most of them, but also ARM32, ARM64, PowerPC 64, and x86-32. So to look in a little bit more detail of what happened here, we can look at the analysis phase, which is the first step it does. And here, the CI goes to your project, and it looks at all the opam files, and it performs an opam solve against each of the possible supported platforms on CI. And some of these will succeed. Here, for example, we found a solution using OCaml 4.11 on Debian, and others will fail. For example, OCaml 4.04 cannot be used with this repository. And if you want more information about exactly which versions it chose or why it couldn't choose them, you can scroll down further. This is showing the packages selected for 4.10. And if we scroll down further until we find one that doesn't work, here, for example, is when we try to find a solution using OCaml 4.07, and you can see that many of the packages here simply require OCaml 4.08 or later. Once the analysis phase is complete, then it performs the individual builds. There are various lint steps, for example, checking the documentation, checking your code using OCaml format if you've enabled that for your project, and linting the opam files. But most of the work of the CI, of course, is actually just building and testing the software against each of the supported platforms. And when you look at one of them, you'll see that one of the first things it displays is a Docker file, which it is going to use to do this build. And you can take this Docker file and you can run it on your local machine if you want to reproduce the build exactly as the CI would do it. And this Docker file includes the exact hash of the base platform it's using. It includes the exact commit it's using from opam repository to get the dependencies, and includes the exact versions of every package it's going to test against. And in fact, it actually includes a complete shell command that you can just post into your shell to do this build. Another interesting thing that's worth pointing out is that when this fails, it doesn't just say build failed, it can usually give you a useful error message. And that's because we have a large collection of regular expressions that match various ways that OCaml produces errors. Errors from the opam compiler, errors from dune, errors from opam, and so on. And in this particular case, we can see that the change I've made does not work on OCaml 4.08 or 4.09 because I'm using a function that didn't exist in those versions. So I should either stop using this, or I should update my OPam files to specify 410 as the minimum version. And you probably noticed that this build was performed very quickly, and that's because the build machines already had all of the dependencies already cached, and they were therefore able to just reuse that from the previous build. And this is not always the case. For example, if you have changed your OPam file, then it will have to reinstall all the dependencies. Or it may be that they've just been expired from the build cache. But generally speaking, if you are iterating on a PR, if you are submitting a PR and then modifying it, finding a problem and modifying it again, then in that case, after the first time, you should find that the cache is hot and all the builds should go very quickly. Now, this web interface is actually implemented as a separate service that communicates with the main CI service over Cap'n Proto RPC. Cap'n Proto is a really nice RPC system. It's very fast, provides great security, and we have an implementation of it from the Mirage project under Mirage Cap'n P RPC. And in OCaml-CI, we're using this not just to provide the web interface you've just seen, but we also have a command line interface that can be used for scripting, and we have an interactive terminal UI. One unusual feature of the CI is that because it's reading your OPam files and it knows what your project's dependencies are, it can automatically rebuild the project when they become out of date. The CI monitors OPam repository, and whenever a new PR is merged into there, it will rerun all of the analysis jobs and look to see if any of them have changed the selections as a result. If they have, it will redo those builds. And this graph here shows a fairly typical example of OPam repository being updated. A PR was merged to master at 1902, and the CI kicked off 750 new analysis jobs, one for each of the branches and PRs that it was monitoring. For each of those PRs, it performed 19 separate OPam solves, one for each of the platforms that it tests against. And as you can see, it took it about 18 minutes to find all the changes, all the jobs that needed to be rebuilt. That's doing about 12 OPam solves per second on a single computer. And the way we managed to do that so quickly is by using a new dependency solver. So what we did was we took the package dependency solver from the Zero Install project, which is actually nicely functorized and doesn't actually depend on the rest of Zero Install at all, and we applied that functor to the OPam package module. And we found that this solver is able to find solutions much more quickly than the standard OPam solvers. In fact, when we tested it on every single package in OPam repository, not a single one of them took more than a second to produce the solution. And we've been using it for a few months now. It's pretty well tested. We're using it in OCaml-CI. We're using it in the Duniverse tool, which is a really useful little tool for pulling in all the dependencies of your project into your source directory so that you can do a Dune build across the whole thing all in one go. And we're also using it in OPam Health Check, which is a bulk build that we do every few days, testing every package in OPam repository. And that was previously using the Z3 solver, but using this solver it was actually faster. And if you want, you can also run it from the command line. It's available in OPam. Here I've asked it to find a solution for UTOP and OCaml 410.0. And as you can see here, the solve took 0.22 seconds. In fact, it actually found the solution in less time than it took to initialize the OPam library. One thing you'd often like to do with CIs is to reproduce a build locally. And I've already shown that every CI build includes a Docker file that you can copy and paste to reproduce that particular build. But another thing that you might like to do is to actually run the CI itself on your local machine. You can do that by cloning its repository and running the OCaml-CI service command, although if you want to do that, you will have to register your own GitHub app. So we also provide an easier way, which is the OPam-CI local command. You just give it the path of a local git clone, and it will run the CI just on the head commit of that repository. And when you do that, it will provide you with a little web interface, and here is a screenshot I took from that, showing the pipeline that it runs. Over here on the left, it's pulling in some Docker base images. You can configure which platforms you want. You don't necessarily want to pull in all 19 platforms. I've configured it here just to pull in 3. For each one, it queries OPam to find out details of the distribution name and so on, which are needed for the OPam solve. Below that, it will clone OPam repository to get the metadata about the dependencies to find out which versions are available. And then finally here, it's actually monitoring the local repository. This is querying to find out which branch your repository is currently on, and this is querying to find the head commit of that branch. And all of this is input into the analysis phase that we saw earlier. In this case, the analysis phase determined that OCaml 4.02 wasn't supported, but it has produced builds for 4.09 and 4.10, as well as some lint jobs. For example, this build here has failed, as shown in red. You could click on that and actually see the log and interact with it. And this is really useful if you want to extend the CI. If you'd like to contribute some improvements to it, you can just use this to test your improvements locally. Now, that diagram that we just saw is an example of an OCurrent pipeline. OCurrent is an embedded domain-specific language for writing pipelines for keeping things current. It's a form of incremental computation, like Jane Street's incremental library or Bunzl's React library. But it also makes it very easy to do static analysis, and that is how we're able to generate these diagrams that show what it's going to do, even if it hasn't actually completed all the steps yet. And here's an example of a really simple OCurrent pipeline. We get the head of a local repository and call that source. We use Docker to build the source code to get a Docker image, and then we run a make test command inside that image. And that pipeline will automatically generate the diagram shown here. And by the way, the colors here, green indicates a step that's been successful, orange indicates a step that is currently in the process of being built, and grey indicates a step that cannot run yet because its inputs are not ready. So OCurrent provides a language for connecting these boxes together. To actually get these primitive operations, we have packages available for interacting with Git, GitHub, Docker, Slack, and OCluster. And you can also define your own primitive operations very easily. There is a wiki in the OCurrent repository with tutorials, and there is a skeleton project which you can use as a starting point for your own pipelines. So here's the actual pipeline used by the real CI service. We're putting on a lot more images on the left than we were in that smaller pipeline we saw. And we're also querying GitHub for a list of accounts that have installed the GitHub app. For each of the accounts, we get a list of the repositories. In this case, I've expanded the Mirage organization. And then for each of these repositories, we get a list of the PRs and branches that need to be tested. I've expanded the capnp RPC repository. And then for each PR and branch, we fetch the source code, and then we run that same pipeline that I showed you before, where we do an analysis, and then we do the builds. And then finally, we push the status back to GitHub. And there's an admin UI that you can add to any OCurrent pipeline that will automatically give you a web interface that will show you your pipeline graph, allow you to view the logs, do queries over previous results, and configure the regular expressions used in the log analyzer. Now, writing CI pipelines is not the only possible use for OCurrent, and I wanted to just show you a couple of other uses we found for it. The first is a pipeline that we use for building the Docker base images that are consumed by the CI. And this is a pipeline, it builds a wide variety of different combinations of platform, like Debian, Ubuntu, Fedora, architecture, x86, ARM, PowerPC, OCaml versions from 4.02 to 4.12, and compiler options. And every week it builds these images and it pushes them to Docker Hub. And if you'd like to use them yourself, you can run a command like this. So this is docker run OCurrent/opam Debian 10 OCaml 408 AFL, and that will give you a Docker container that's based on Debian 10 that has OCaml 4.08 installed and compiled for fuzzing with AFL, for example. Another use we found for OCurrent is for deploying services. We have a deployer pipeline that watches the live branch of various repositories, and when it sees a new commit pushed to the live branch, it will build it, push it to Docker Hub, pull it from Docker Hub onto the build machine, and update the service there. And while it's doing this, it will send updates of its status to Slack, so we can see what it's doing. In fact, for the CI, we're actually watching 3 different branches. There's a live engine branch, which we use to deploy a new version of the engine. There's a live dub branch, which we use for updating the web user interface. And there's also a staging dub branch, which allows us to experiment with changes to the web UI before we're ready to push it live. And finally, the deployer also watches all the other branches and PRs in the repository and just builds them just to make sure that they can be built, and pushes the status of that back to GitHub. And the final component of the system is the OCluster build scheduler. This is a little OCaml service that runs on one machine. It takes job submissions from clients such as OCaml-CI and the base image builder, and it distributes them to various worker nodes. This just makes it really easy for us to add new machines to the build pools when they become available. Okay, so now I'm just going to give a quick demo of the OCluster system. First of all, you need to run the scheduler, and it takes a few arguments. You need to tell it whereabouts you want it to create its private key. You need to tell it what address to listen on for incoming network connections. The scheduler is the only component in the system that needs to accept incoming connections. You need to tell it its public address, which is where it suggests other services should connect to it on. Here I'm just using localhost, but obviously in a real system you'd use some kind of public address here. It needs a directory in which it will store the database, telling it which jobs it has previously assigned to which workers, allowing it to assign similar jobs to the same worker in future and benefit from caching. And then finally, you can specify whatever set of pools you want in your cluster. These names can be whatever you like. Now we can see it's generated a set of 4 capability files, and each of these grants access to some service within the scheduler. For example, the submission capability gives its holder the ability to submit things to the cluster. The admin capability gives the ability to run administration commands, and the pool capabilities give the ability to be a worker and to register to a pool to accept jobs. So let's just take a look at one of these capability files just to see what's inside it. So it's a URL, and it has several parts. This part is the address which the holder of the capability should connect to access the service. This part is the fingerprint of the server's key, which allows the client to check that it is connected to the right service without the need to set up any kind of PKI or create certificates and sign CAs and things like that. And the final part is this Swiss number, which identifies which service to use, and also it's a secret which grants you permission to use it. And the other cap files will be the same, except that this Swiss number at the end will be different. So let's try adding a worker to our cluster. We'll say OCluster worker. We need to give it permission to connect. I'll connect it to the x86-64 pool. And we need to give the worker some unique name. This is mainly used for monitoring, so we can actually tell when a machine is running out of disk space or whatever. So that is now connected to the scheduler. Okay, so now let's try using our new cluster. We'll use the OCluster client command. We'll submit a job. We'll need to give the client permission to use the cluster by giving it access to the submission capability. We'll need to say which pool we want it to use. I'll use the Linux x86-64 pool. And we need to give it a description of the job we want it to perform. And in my case, I'll ask it to build a local Docker file. And here we have a client connecting to the scheduler. The scheduler hands the job over to the worker. The worker is executing the build, in this case using Docker, and streaming the logs back to the client. So in summary, OCaml-CI provides a fast build and test pipeline for OCaml projects. But you may find that the components it's made of are also useful to you individually. The diagram on this page shows the ones we've looked at: the web user interface, the command line interface, the CI engine, the new opam solver, and the OCluster scheduler. And the arrows represent the cat and Proto connections that tie everything together. All of this software is open source, and I've included links throughout this talk. And if you would like to get involved, please get in touch.